I'm Alex. I'm a PhD student at KIT here in Germany, and I'm speaking today on behalf of the b2luigi developers and maintainers. Jonas is also here, so questions can be about anything later. Yes, so short outline of the talk. First, I want to introduce why we use workflow management and high energy physics. I will define a workflow, how I see it for now. Then we talk about a few basics of Luigi, which are necessary to understand the further steps of introducing b2luigi, but of course to understand the whole concept of how this package helps us to define the dependencies of our workflow. And in the end, I will show you a few examples how b2luigi is implemented currently at Belle II. Sadly, I don't have examples from other experiments, but I hope, of course, after the presentation today and a few discussions, maybe the package can be applied at other experiments as well. And then, yeah, we have a short summary and discussion points. So to define a workflow, I want to highlight a analysis and very briefly in 5 steps. And for purposes, the analysis always starts at some sort of data. So we either have the Monte Carlo production of our data, or we have actual measurements from the detector. Then the data goes through several pre-processing steps, where we do, of course, cleanups, where we then transfer all the measured currents into hits objects, and we then further work with the hits objects until we can come to a very crucial part, the reconstruction in analysis. This is when we go from hits in the detector, in a tracking or calorimeter, for example, into physics objects. So meaning we're now talking about tracks or clusters in a calorimeter, and then from this physics objects, we then derive, of course, quantities like energy, momentum, which we then can use for our selection processes. If analysis does a very specified selections, of course, always with the goal in mind to reduce background as much as possible by keeping as much as possible signal alive. And as soon as we have a selection, we can then go and start with the statistical analysis, perform fits, and so on. Can derive quantities or calculate upper limits if necessary. So, and here we come now to as you see, this was very briefly summarized of what analysis looks like. This analysis comes with a few computational challenges that I will briefly outline. First, I think this is what everyone is in contact with. Of course, these 5 steps are nothing near the reality. In reality, in between every step, or also each step by itself, is very complex and consists of many different steps, of things that can go in parallel, of things that have to be reused, and so on. Another key challenge, of course, when we talk about data taking, is scalability. We, of course, want as much data as possible, so we're recording data every second of every day, and this leads to more data, but also we develop more and more analysis, meaning we have more and more selections maybe ongoing on the same data. Another key challenge is reproducibility and reliability of my workflow. Of course, if I do a Nobel Prize winning discovery, as for example the Higgs a few years ago, then I do not want to miss the Higgs the very next day, because my workflow somewhat is not reproducible. And of course, the last a more technical issue is resource management. Due to the big amount of data and Monte Carlo that we process every day, we of course mostly cannot do this on our own resources like the laptop, but we rely on bigger systems, grids, and batch farms that we can use to process our full workflow. Introducing here now Luigi, just very, very briefly. Luigi is a tool to enable you to build a pipeline, meaning you can break down each and every step in this analysis chain and make those steps be executed in a given order. So as an analyst, you want to define different dependencies of different steps, but you also want to include all the features that you need along the way. And Luigi helps you with the management of these dependencies. It helps you with the visualization in some sense. Of course, nothing ever goes right the first time, so it also helps you with handling failures during a pipeline, and it comes with a very neat command line integration. It was initially developed by Spotify, which you also see in some parts of the code, that it was not built for high-energy physics, but we can still use this. And here you can see on the right now, like the basic hello world example of Luigi. Of course, it's much, much, much more. But for the following parts, I want to introduce the base concept of Luigi, and it's a so-called Luigi task, which helps you with all the things on the left. So basically, in a Luigi task, you need more or less three methods. Of course, some of them can be omitted in special cases, but the key components are the run, the output, and the requires. So basically, the run method does exactly what you want to do in your task. So here you define all the logical steps that you want to do a fit, do a plot work. It can be as complex as you want it to be. And this run method will have a dedicated output of some sense. So you will have some selection that you store in a file, like a CSV or JSON or any other data structure. And this you define with the output, and the output of the task helps to get the stage of the current task. As soon as the output is present, a given task is counted as completed. And now to build a dependency between different tasks, you can define require methods that yield the other tasks. So now the output comes back into play. A task is completed as soon as the output is present, meaning this current task, my task, will only run as soon as the output of the other task is also present, because then the dependency is fulfilled and the task can start. Another small comment about the Luigi. To do all this dependency resolving, the Luigi comes with its own scheduler, and the goal of the scheduler is to build this big graph, which will then be executed. So in total, the user, by writing the task, by writing the outputs and requires methods of each task, encodes the dependency of the tasks, and the scheduler then builds a graph and ensures on the one side that, of course, every time task is run, and that multiple workers don't execute the same job at the same time, because this would only lead to multiple use of resources that can be used otherwise. So essentially, we have a central planner instance that spawns different workers that then make sure that which task is done, which task has which state currently, and which task can each worker run. Also, a very neat thing from Luigi is this graphical visualization. This is the example from the documentation you can see here. So we have some sort of output task that depends on a series of other tasks that again have dependencies on their predecessors. Coming now to why do we need to extend in this, especially in HAPS, in high-energy physics. And the first reason is, of course, that we have many jobs. Usually we have a large amount of data. we can actually use the term big data. As we saw before, each step in our analysis can be described in many different steps. So we have a lot of jobs. And for Luigi, this naively comes to a challenge that each running job is equal to a running process. And now, of course, a common limitation on any resource that we have access to is that they mostly limit the number of processes per user. So what we do within b2luigi is we abstract this problem a little bit, and what we can do is we take only the submission as a process, and then spawn the jobs on within the batch system on the node, so somewhere in the batch system, and then they run there as a process. So in turn, we only have a single process on our submission machine, and all the workers that are running our tasks, they are running as a process on the worker node and not in our submission machine. Also, with many jobs come many tasks, and here comes another challenge that we face in Luigi, that for now adjusting the different tasks for example, different batch systems, it has to be defined in an instance of a class, and meaning if I have a non-batch problem and I then want to make it into a batch process, I have to redefine the class. So of course, a little bit tricky if I have many tasks, and the current solution is that you again abstract the batch submission such that you can do the submission with a single argument in a single function. We will talk about this later. Which brings another cool feature of this, because it's also not naively implemented in Luigi, is I do not know which batch system I want to run. Maybe I have access to more than one of them. So I could have, for example, access to an HTCondor queue, but also to LSF, and to change in between different batch submission systems, at least a few years back, was very difficult in Luigi, and in b2luigi it's possible with only a single config variable. So you can say I want to run an HTCondor, change one line of code, and it will run on LSF, for example. Before we dive into a few examples, I just want to make a few remarks. b2luigi was written by a group of PhD students to help with their analysis. So the goal was just to make the everyday life a little bit easier by taking care of certain processes that were a little bit harder in Luigi. But I also want to point out here that it was definitely not a goal to invent the next workflow management system, because if you spend a little bit of time of Googling, you will see already that there are a lot of different solutions. So no one wants to reinvent the wheel again, but just basically provide a wrapper for an already very good tool. Meaning b2luigi comes with a lot of helper functions on top of Luigi, and it's very easy to transition between Luigi and b2luigi, mainly due to the fact that in our very first init, we just import Luigi from Luigi star. So every functionality that is in Luigi is also in b2luigi. We just overload a few functions that are necessary to make the changes that we want to have. Sadly, most of the, or basically now all of the initial developers and maintainers of b2luigi have either left academia totally or are progressing their career a lot. So for a very short amount of time, b2luigi had no real development anymore ongoing, and the Belle II collaboration has offered to be the official maintainer of this package. meaning we have now a completely new team of developers and maintainers. And of course, we now target a collaboration by use, but we also want to keep b2luigi as simple as possible, such that it's not tied down to our experiment that we would not present here. So we try to make b2luigi as experiment agnostic as we can. Yes, just for people that go through slides, I want to highlight just a few links. So you can find us in Piper. You can just install b2luigi very easy via pip install. We have a GitHub repository. A quick remark here: it's a mirror of our internal GitLab, and we have not yet installed a GitHub pipeline. So we will work on mirroring the GitLab to GitHub and vice versa in the future. But currently, if you would open a pull request on GitHub, we report it back into our internal system where we then have everything set up, meaning also the pipeline. Yes, so diving in with a example of how a b2luigi task can run. By the way, from here now on, I will not make the big difference between Luigi and b2luigi. I will just talk about it as one project, mainly seen from the b2luigi side. And you can see here just a simple task that does nothing fancy, just generates a random number and writes it into a file and saves this file. So a few key points that I want to highlight here is that in contrast to Luigi, the syntax is a lot simplified. So we have methods like get output file name or add to output, which just help the user to define the output input structure a lot by only giving keywords and not having to think about the entire path. You can, for example, write this everything down in a script.py, execute it with Python. And to bring this into batch submission, into batch mode, the only thing you have to do is to add this minus batch, or you add a batch equals true into the process function as we've seen before. Neat thing, but here, of course, it's this is inherited from Luigi. Batch jobs are only scheduled when all dependencies are fulfilled. And if you run in batch mode, there's only one process on the submission machine, which saves local resources. As soon as the task is done, is run, you see somewhat like in the upper left, this is the output of the task. It's a quick summary because Scheduler permanently keeps track of the state of each job. It takes action if needed. For example, if a job fails, you can resubmit it as well, or you can make retries with the job. And here on the left, you can see how this looks like in this example. Here we have our simple script that we just saw on the previous slide, and we have a folder results by the definition that we set in the b2luigi settings. As a result, here should be results, and here you see a directory for every parameter where the output of every parameter lies. And this, of course, is due to the reason that we talked about before. A job is done if the output file exists. So unique output names for each job. And the easiest approach to solve this is to make them dependent on the parameters, because the parameters differ. So b2luigi creates a folder structure for each parameter. Very important note here is that it only job counts as successful if the output exists. It does not care about the content of the job itself. And this is one of the biggest differences to Luigi. We have a settings system which helps you to configure your task to your specifications. And you can control something like the batch system size, the output and logging paths, the environment, and other workflow-specific settings. And it goes down from, we have 4 different ways of setting up settings. You can make it an attribute of the class, a property. You can use, as we've seen before, the set setting method, or you can provide the settings.jsons and priorities from top to bottom. So you can make first task specific settings and then global settings. If we now look at a little bit advanced structure here, now we have the second task built on top of the first that I've shown before. It requires the previous task by calling it with the method clone and providing it the parameters that we defined before. So it will look for the existence of the finished task before. If this is matched, it will execute its run method. Just to make sure this works, we can use little features to show the output feature of a b2luigi process, and it will just outline you what the output structure of the entire chain is. And we see, okay, from the first part, from the required task, every file is present. The only one that is missing is the average task, basically our wrapper task. So when executed, the outputs will not be recomputed, but then used for the average task. Talking now also about a little bit of batch processing. So the initial motivation of b2luigi was to make batch submission easier. And that's what was tried with very simple settings, like just a batch system attribute where you can use the name of the batch system. You can provide settings. This, of course, then depends on the batch system that you're using. And we currently fully support HTCondor and LSF, and b2, which is just basically our submission tool from Belle II to submit to the VSCG. A few challenges that come with batch processing and that are solved with b2luigi is first the environment. Of course, you cannot always assume that you have the same environment on the batch side as you have locally. So you can provide an environment. The easiest way is just by providing an environment script which is executed for every task on the batch side. And also, what you cannot ensure is that you have the same locations locally and on the batch system. And for this, we provide a few directory paths that you can set for your task to make sure that the output is stored and copied then back locally correctly. So, for example, in this HTCondor job, we could globally set that for every task. The setup.sh script is executed. We specify, as we've seen before, that the result here is just a simple results. So it's a relative path. This results directory will be then created at the execution location of the script. Here I also show a small feature that I personally use a lot. That's the wrapper task. The wrapper task does not need a run or output method. It's successful whenever the output of requires is already present. So this one will be run locally and will yield my task, and my task will then be processed on the batch side, more precisely on HTCondor. And what we also, for example, use here is an executable settings, which will make sure that the executable Python is used that we want. And in this example, will be defined as an environment variable in our setup.sh script. Just to give you a brief idea of how to use this. Now I want to go quickly over a few examples. I think I skipped this one. But we at Belle II, we use this already collaboration, right? We have, for example, the validation interface for the Belle II experiment, or short VIBE, that basically is run for every processing of data Monte Carlo. And the logic is that you create a analysis script that creates n tuples for you. You do this in parallel for data and Monte Carlo, which then gives you n tuples as an output, and then you can run whatever process you need to validate. Mostly it's some fit. For example, you want to make sure that the D star mass is always correctly reconstructed, or the trigger efficiency didn't change, or is more or less equal between data MC and so on. Also, a very cool framework that we have is a systematic correction framework. This is a two-stage algorithm. First, we have a centrally run job. So it's basically the left side of the previous plot I've shown. It's also just the n-tuple production. Also, it's run for every campaign, every experiment, and run, and centrally produce, and it's running on or with gbus2, meaning on our grid system. And then users can interface the outputs with their own scripts. This when they actually create the data in Monte Carlo corrections themselves. So they can provide a script that fulfills several steps, and this can then be run either locally or with the use of other batch systems like HTCondor or LSF. For example, this would be such an output. We have the efficiency of a PID cut. What I really come to like about this framework is how easy the developers implemented it. Basically, all the users have to provide is this short list of parameters. This then is piped into the workflow, which uses b2luigi to schedule all the different steps in between. So to summarize, b2luigi provides a simple and flexible implementation to make your every analysis workflow life a little bit easier with the help of batch systems. And this was mainly achieved through the introduction of the settings, which lead to a quick change in submission strategy, and makes the code and execution a little bit simpler than it used to be before. And I want to finish with a few questions for discussion. There are a lot of different workflow management systems. I want to ask if we maybe want a common standard that we use in high-energy physics. Not because everyone uses like Airflow, Spark, maybe the CMS experience, and now use Law, which is very similar to b2luigi, but maybe we can somewhat agree on a common standard. And also, it's a very general question: is if we can make these the packages that we write fully experimental agnostic, which of course is connected to the first question. Yes, thank you for your attention.
Okay, yeah, thanks very much for the talk. So we have maybe 2 minutes for questions, so maybe we can ask at least one. Let's see. So I don't see any hands, so maybe I will take chair privilege to ask one. So this was a nice talk. I had just a kind of a general question, given that Luigi kind of comes from the broader open source world, and I assume that there's many other like non-physics people out there who would want to be able to leverage batch systems in the same way. Have you shared the existence of b2luigi with other Luigi users? And if so, are they interested in it?
No, we have not, or it is as of my knowledge, we have not shared this before. We as Belle II took over this year, so at least this year, no bigger efforts were made. I'm not entirely sure if this is what we are targeting for, because we really target for HAP analysis workflow management. But I would be open to, of course, share this outside of this community.
Yeah, it seems like if there's many people across science and even industry that would be able to provide maintenance, that might be a good thing. Okay, so we're a bit out of time, but I will just kind of take a quick stab-in comment at the 2 bits of discussion there. So are there many other workflow management libraries? I think in addition to Luigi, we also have like SnakeMake and Common Workflow Language, CWL. So although CWL is more of a standard, which so you have different implementations of CWL, and SnakeMake itself is actually able to has an agreement with the CWL standard. So I think maybe while I understand that Luigi, takes a bit of a different tact there, it might, given that there was some discussion at CERN in January around the meeting, the FAIR-OS HEP meeting on workflow languages for physics analysis, where Luigi was discussed some as well. It would probably be good to have some continued discussion there. And when it comes to making things fully agnostic, I hope so. It would seem very, very poor for us as a broader community if we can't. So yeah, hopefully we can continue pushing forward on those barriers.